In today's lecture, we're going to build on our previous lectures and our discussion of the infinite square well and the finite square well potentials and try to build some intuition and some qualitative expectations for what we expect those energy eigenfunctions to be for arbitrary wells. What do we expect the wave functions of bound states to be? And to do that, we're going to sort of look at what we've just done, which is these two square well potentials. And one of the things we notice is they're symmetric potentials, and they have a constant potential inside the well. And that means, and what we got in both situations is these sort of standing wave eigenfunctions inside the well have a constant wave vector k. They have that constant wavelength and everything associated with that. And what's going to be different for arbitrary wells is that's not necessarily the case. So if we have, sort of one of the simpler examples of an arbitrary well would be a sort of square well with a step inside that well. So we have infinite potential well for x below 0, infinite well or infinite potential for x above L, and then inside that well, we have a potential of 0, and then it jumps up to some value V naught, say. So what do we get when we have something like this? Well, first, we're going to do the same thing that we did when looking at the other wells. We want to solve the energy eigenvalue equation to determine both what those eigenenergies are, what our spectrum for that well is, and what the wave functions of those bound states are, right? And we're going to do the same thing we did with the finite well, where we're going to split this into regions. Um, for x less than 0 and x greater than L, we have sort of the trivial case where we know that that wave function has to be 0 because there's an infinite potential there. So if we had a wave function, a finite wave function in there, we'd essentially have infinite energy. So we know that that has to be 0. If we look at what I'm going to call region 1, from 0 to L over 2 in this case, we have a potential equal to 0, so our differential equation reduces to this, where we have some wave vector k1 equal to just 2m, the energy eigenvalue, divided by h bar squared, all squared. And we know this. This is the exact same differential equation we had for our infinite potential well. So we're going to have the same solution in region 1, where it's just going to be a sine k1 times x. We can get rid of the cosine term in that general solution because we know at x equals 0, that wave function has to be continuous. So it has to be 0 there. So that cosine term has to go to 0. And we have that solution, right? What about in region 2 over here where we have a potential V naught? Now, we're going to consider cases, for the purposes of today's discussion, we're going to look at bound states with energies greater than V naught. There will be bound states down here in this sort of smaller well, but let's focus on ones with energies above V naught. And if we do that, our differential equation looks like this, right? Very similar to what we've seen before. Our second derivative ends up being, this is the exact same differential equation we had here. It's just our wave vector is different. It has this V naught term. So this wave vector is actually going to be slightly smaller than that wave vector, which, is it's a significant difference in our solution. But the differential equation is the exact same. It's going to have the same solution, except for it's not starting at 0, so we can't necessarily get rid of that cosine term in the solution. So our wave function in region 2 ends up being this. Now, we have our wave functions, the form of them in the different regions. We have to impose our boundary conditions to solve for some constants, right? First one, wave function must be continuous. So if we look at the boundaries at L over 2, the wave function in this region must meet the wave function in that region. And another one at x equals L, the wave function in region 2 has to go to 0 to be continuous with the wave function where the potential is infinite. Our other differential, or our other boundary condition is that the derivative must be continuous, unless, of course, the potential is infinite. So that means at L over 2, the derivative of those wave functions must also be continuous. They must equal. The derivative of the wave function in region 1 must equal the derivative of the wave function in region 2 at x equals L over 2. These three boundary conditions give us three equations. The first one uh, gives us just set those two equal to each other when L equals 2. Likewise, if we take the derivative and evaluate it at x equals L over 2, we get this equation. And then finally, the boundary condition that the wave function has to be continuous at x equals L gives us that equation. So we've got, following the same technique we used before, just really quickly went through it. We've spent enough time sort of doing this before. We have three equations that we can solve. Unfortunately, we have more than three unknowns. We have A, B, C, K1, and K2, which are connected by the unknown energy that we're trying to solve for. But we have four unknowns, three equations. We can't really solve that this analytically, but we can sort of do a similar thing that we did with the finite well, which is, we can eliminate A, B, and C from these equations. And that gives us this equation. There's a ton of trig and different things to get to there that I don't think's, valuable for us to spend all the time going through that in the lecture. I may ask it on the homework. But we end up with this transcendental equation where we have just K1 and K2. If we were to say choose a K2, which essentially amounts to picking what this V naught is, we can sort of think about this and plot it. Ultimately, we're going to have to solve this numerically, though. And when we do, we get something like this. Now, hopefully, the goal, one of the big takeaways of this video is by the end of it, I want us to start to develop a good idea of how we can sort of predict just intuitively what we would expect this wave function to look like. So numerically, this is a numerical solved solution for this potential well, and it looks like this. We're looking at the 7th energy level. So the n equals 7 sort of eigenenergy bound state. And one of the first things we notice, or one of the things that you can notice from the solution, is that the number of antinodes matches the energy level, just like we had with the infinite well and the finite square well potential. Our bound states, there's going to be a certain quantized number of these bound states, and each one increasing in energy is going to have an increasing number of antinodes. So this is the 7th energy level, and you see 1, 2, 3, 4, 5, 6, 7 antinodes in that bound wave potential, right? So the number of nodes, or antinodes rather, should match the energy sort of level we're looking at in our bound states. Another thing has to do with the wavelength, right? If you remember, the solution in these bound states had that k squared wavelength, and in general, those that k squared constant in the differential equation, where k was a wave vector, and the general sort of idea behind a wave vector is it relates to a wavelength, right? We have this 2 pi over lambda relationship for a given a wave vector. And in that differential equation, that wave vector was equal to this, that it depends on that potential. So here, where in region 1, where we had the V equals 0, we have a larger k, or smaller wavelength, than we did in region 2, where we have a larger V, smaller k, larger wavelength, right? And you notice that we have a short wavelength here, larger wavelength there, right? Another thing we have is the amplitudes changing in here, right? And this sort of ties in with the wavelength sort of idea, right? The wavelength's related to curvature. A short wavelength means a lot of curvature in this wave function at that point, and a larger wavelength means less curvature. If you think way back to when we first started solving for these eigenenergy value equations, we know that this is related to the kinetic energy, right? The total energy minus the potential energy is related to the kinetic energy. And there was this relationship where more curvature related to more kinetic energy. So this means there's more kinetic energy when the particle on the left side of the well than on the right side of the well. And if we think about what the amplitude of this wave function means, we square it and we get the probability density, right? So a larger amplitude means you're more likely to find, if you were to measure the position of that particle, you're more likely to find the particle at regions where there's a large amplitude of wave function. Putting this all together, it means we are more likely to measure the particle over here than we are here. And classically, this makes sense. If you were to, have a ball with some energy, this much energy in it, it would be moving really fast on this side. It would slow down over here because some of that energy would be in potential energy. So we'd have a ball that'd be moved fast here, slower here, fast here, slower here. And what that means is if you were to just pick a time at random or measure the position of that ball, it would be spending more time on this side. So we are going to expect it to have a larger amplitude of wave function on this side because that relates to the probability of measuring that particle, right? So again, we can see these sort of things that we should be able to intuitively, once we're comfortable with it, think about and sort of get a good qualitative approximation of what we expect those wave functions to look like. The other thing we have to check is that those boundary conditions hold. This wave function has to be continuous in both the value of the wave function and the slope as we cross this boundary, and it has to be continuous at the actual boundaries. These ones go to infinity, so that those wave functions must go to 0. If these were finite wells, there'd be that exponential decay to 0 as we penetrate into that potential barrier, right? So hopefully, if you think about these things, we can then start to think about arbitrarily drawing wave functions or predicting what the wave functions will look like in arbitrary potentials. So here we have everyone's favorite harmonic potential, and we notice the bound states 1, 2, 3, 4 are drawn here. Each one has a node, antinode rather, for whatever energy level it is. The wavelengths are subtly changing as the potential goes out. It's difficult to see that because it's sort of continuously changing. The boundary conditions, we have these exponential decays into the barrier, but continuous across the barrier. Likewise, this sort of triangular potential, which a lot of the times electrons in the transistors get modeled in a potential that looks like this. You see, again, antinodes match the energy level we're looking at, that exponential decay into the finite potential well, and the wavelength sort of getting longer as the potential increases, right? There's a shorter wavelength here, but it gets longer and longer as that potential increases. And you can build on that and start to imagine what these sort of wavelengths will look like, right? This one, E5, would have, that's inside this deeper well here, it would have some exponential decay, and then it would have 5 antinodes. I didn't count how many, I just tried to sketch through there. But it would have 5 of those and then exponentially decay into here. E10 would have 10 antinodes, again with an exponential decay on this side. And you can sort of intuitively start to draw this. And we'll do some exercises in our synchronous meetings as well as on the homework. But hopefully this is starting to make sense, and with some practice we can get pretty good at it. As usual, any questions or difficulties you're having, reach out to me, and I will see you in our synchronous meetings.